Okay, welcome to the final lecture or two of our course. In this part, we'll finally get to proving the Magyar Stein Wainger theorem for the discrete spherical maximal function. More appropriately, arithmetic spherical maximal function. And the way we're going to do this is we're going to use the high versus low method, which we've already seen in a couple of different instances. So what I mean by high versus low is that we're going to look at the frequency side, and we're going to decompose our operators and or functions into some high frequency pieces and low frequency pieces. But there's going to be a cutoff in terms of what means high versus what means low, and we'll optimize that cutoff to the particular function or operator. Right, so we saw this before in the heart of the wood circle method. The high and low were the minor arcs and major arcs respectively. And we also saw this in the Stein spherical maximal function quite directly with the operators that were labeled high and low. And those were just the Euclidean frequencies, which were the high ones were all the frequencies that were outside of some big ball, and the low ones were all the ones inside some big ball. And but we had a smooth partition of unity to ameliorate edge effects there and ease the technical analysis of things. We'll have the same sort of smoothing come up in this place in our setting today. So just to remind everyone, because it's been a week, right, we're looking at integer points on spheres. So I have a sphere of radius square root lambda. So lambda is going to be some positive integer. And I look at all the integer points on that sphere of radius square root lambda, where the sphere is centered at the origin. And we know there are asymptotics for this. As soon as you have 5 or more dimensions, that is 5 or more variables. Okay. And we use these to define the arithmetic spherical measure, where I just take as my measure the indicator function on the set of integer points on my sphere, and I normalize by the number of such points to make this a probability measure. We do this because we're going to consider the maximal function, and we want probability measures so that when we form the supremum over all the possible averages, we're not weighting some things excessively so that it really, as the number of points on the spheres grows, we're not weighting them more and more, so you're just capturing what's going on at infinity and making it blow up, right? So we're instead weighting things in an isotropic manner, sort of giving each point equal weights depending on the total number of points on the sphere, right? And then we form the maximal function just as before. It's the supremum over all possible averages. Oh wait, sorry, I didn't say the average is just convolution with this probability measure, right? And we have an average for each positive integer lambda. And then the maximal function is formed by taking the supremum over all the possible averages, point-wise. Great, so we've seen this several times. And once again, here's the Magyar Stein Wainger theorem. They say as soon as you have 5 or more dimensions, this discrete spherical maximal function is bounded on LP of ZD. That is, if you take a function f defined on the integer lattice ZD, and it maps to the complex numbers, then whenever you measure the maximal function applied to that function, the maximal operator applied to that function, measured in LP, it's bounded by a constant times the original LP norm of your function. And this is for all p bigger than some threshold that depends on dimension. For us, that's p bigger than d over d minus 2, where d is the dimension. And we've seen already that this is sharp in both the dimensional aspect. It fails whenever d is less than or equal to 4 for any finite p. And it fails for any p less than or equal to d over d minus 2 when d is 5 or more. And the way we're going to prove this is we're going to prove a restricted weak type estimate, actually. That is, for each exponent above our threshold, this Magyar Stein Wainger threshold of d over d minus 2, we're going to prove a restricted weak type bound, which is indicated right here in the middle. And oh, that should be an M. This isn't quite the Magyar Stein Wainger theorem. I said that the Maxwell function is bounded on LP for all p bigger than that, but the real interpolation method allows you to fill in the gap. In fact, because if you take any p bigger than d over d minus 2, there's some other smaller q between d over d minus 2 and p, and we know that it's restricted weak type at that q, and it's also strong type at infinity, right? We've seen that these maximal functions are always bounded on L infinity. So all you do is you do the real interpolation method that tells you your strong type for every exponent between q and infinity, and that included the p that we started with. But q is also above d over d minus 2, and so you just pick some other exponent that's smaller than that, and you keep going until you get, and you get all the way down to d over d minus 2, but you cannot actually include d over d minus 2. However, ENS, you did prove this endpoint bound with a modification of our argument, and I'll point out where that differs. Okay. So just to remind some notation from previously, we always have this character we're using, e to the minus 2 pi I z, and it makes sense in a variety of spaces. The continuous Fourier transform is done with a tilde, whereas the discrete one, the one on ZD, is done with a hat. But we also do, in an abusive notation, also do the same on TD, where it's really the inverse Fourier transform from ZD. Okay. These are defined as on the page. So we saw in previous lectures that an important ingredient for us is an approximation formula due to Magyar Stein Wainger. And that approximation formula is for the multiplier of the average, right? So our convolution, our average is a convolution operator. There's a kernel attached to that convolution, which is sigma of lambda. And the Fourier transform of that is our Fourier multiplier. It's this exponential sum in the middle. And we proved an approximation formula for the unnormalized measure, which I'm just calling the indicator function of s of lambda. And it's that exponential sum at the bottom. Right. So once we had defined our Gauss sums, and we fixed our smooth bump function, we were able to show the following approximation formula. Okay. It says that the Fourier transform of the indicator function of the set of points on the sphere of radius square root of lambda centered at the origin has the following asymptotic formula. Up to some error term, e of lambda, it takes the following shape, where we have a Gauss sum coming into play. We have the continuous Fourier transform of the spherical measure of the spherical measure on the radius square root lambda, the sphere of radius square root lambda, but localized by that little bump function we picked. And this bump function, remember, is picking out rational points m over q, and is saying that we're localized around those rational points m over q for each modulus q here. Okay, and then we have this other linear twist coming from the units modulo q. Now, what we spent all of last week doing was showing that the error term satisfied the following bound. As an operator itself, so since I've defined it as a Fourier multiplier in terms of a bunch of error terms for this approximation, it's, by doing the inverse Fourier transform, becomes a convolution operator. And on L2, we have the following bound. What Magyar Stein Wainger proved is they prove it without this epsilon. They get the exact same formula, but without the epsilon loss. However, we only proved it with the epsilon loss because it was a little bit easier for me. And it didn't require the use of theta functions. Right. Oh, and this was the bound for the dyadic maximal functions. That is, I picked, so I had these little lambda that are running through the positive integers. And I pick now for each, say, dyadic such integer, so powers of 2 to the j, I look at all the lambda in some dyadic window, and that dyadic window is doubling at each stage. It's getting bigger and bigger as I go along. But depending on the width of that window, I get this bound for my dyadic maximal function of the error term. So we need to renormalize this, actually. That was for the indicator function on the set of integer points on the sphere of radius root lambda. Now we need to adapt this to the averages, so we can actually talk about what the averages are doing. All right? And to do that, all we actually do is we just divide by the number of points on the sphere of radius square root lambda. Okay? And up to a error term, which is as good as the error term in the, up to some error term in the number of points, which is as good a quality as the error term for the Fourier transform of the indicator function, we have that the approximation takes the following shape. Okay, recall that this this, what looks like a G of lambda is actually a math frac S of lambda. And that's standing for the singular series. It encodes all the p-adic behaviors for what's happening on integer points in a sphere of radius root lambda. So you notice that this factor of lambda to the d over 2 minus 1 isn't present in the above part, like in the main term. And that's because it was encoded already in this spherical measure, right? Before I had it up here because this is a normalized spherical measure and this was an unnormalized count over here. But now that I've normalized it, it's no longer appearing in front here. And it's just encoded in that spherical measure right there. However, we do still have the p-adic effects coming into play. And it's really important here to remember that S of lambda is always less than or equal to some big constant C and greater than or equal to some smaller constant C inverse, right? Now this approximation formula is for each of the averages. So I've written this A hat here, which is a sort of a standard notation for averages, or for whenever you have a convolution operator to write its Fourier multiplier. I should have really written this as a sigma of lambda. Right, so that's the spherical measure. And now our normalized error term actually takes the following shape. It looks like this, lambda. So the bound is lambda to the 1 minus d over 4 plus some epsilon loss. Now, taking epsilon sufficiently small, we see that as soon as d is 5 or more, this error term is bounded on L2 of zd to itself with a bound that decays depending on lambda. And so this big lambda, I can take it as, say, being powers of 2, and I can sum up now over all those powers of 2 to show that the whole maximal function for E of lambda is bounded on L2. We'll use that in a bit. Great. Are there any questions about the normalization so far? Okay. Well, going forward then, one point that I thought I was going to use last week, but we're actually using this week now, is the transference lemma. So we proved this a couple weeks ago. What it's going to do is basically every time I prove something for q equals 1, I'm going to get to upgrade it for all q bigger than or equal to 1, for all natural numbers. Okay. And remember, this was a very abstract thing. We were starting with something that's acting as a multiplier on a small set. Here's something that's of width 1 over q, a box of width side lengths 1 over q, centered at the origin and aligned with the axes. And it's mapping into linear operators between two finite dimensional Banach spaces. And we show that if I have a bound on RD, then we get a bound on ZD for every modulus q. Okay. Well, actually, in this way I phrase it right here, I've fixed the modulus, and I've shown that this bound doesn't depend at all on the modulus. Okay, which means we'll be able to use it for all moduli q once we set it up correctly. Great. Now, again, we're going to use this by taking our Banach spaces to be little L infinity of the set of integers from 1 to n. So what we do is we truncate the natural numbers up to some big threshold n. That's going to go to infinity. We prove all of our bounds with bounds that don't depend on n at all. And when we do that, we just get to send n to infinity by monotone convergence. Okay, so really, I should, if I really wanted to be rigorous, I should do the following. I should insert some maximal function m of n, which is going to be at each point x, it would be defined as the sup over lambda in the range from 1 to n. of a lambda f of x, right? And then I prove the Magyar Stein Wainger theorem for each m of n. And I prove bounds that don't depend on n at all. Then I say monotone convergence means that I can actually take the lim as n goes to infinity of mn, which actually equals m, because it's increasing monotonically, and conclude the same theorem holds for m. Okay, I'm going to conflate that in what follows by just pretending that I could take n to be infinity in the first place. But really the rigorous argument is to go back and do this. However, that's sort of a standard topic covered in graduate real analysis, which I'm going to take for granted right now. Okay, but that's really the right way to do things. Cool. So what is our first theorem? Before we get to the proof of the Magyar Stein Wainger theorem, we're going to prove that the main term in our approximation satisfies the bounds that we want it to satisfy for the spherical maximal function. And then I'm going to use that and some other information to upgrade to the full maximal function. Great. So what does this mean? I have these operators C lambda A of Q, and these are defined so that the Fourier multiplier was this term sum over M in ZD, the Gauss sum, localized spherical measure, okay, and multiplied by e to the minus a lambda over q. Or actually, why don't I just do this? I'm going to throw it in right here. In between, I should say, right there, I should have an e of minus a lambda over q. Okay. And now I form this maximal function where I take this, I sum up over all a and q. Remember the approximation is a sum over all q and all the units coprime to q. And I form the maximal function in exactly the same way as for the discrete spherical maximal function by taking absolute values for each c of lambda and then a sup over all possible lambda. Our theorem is that as soon as we have 5 or more dimensions, we have the restricted weak type estimate at the endpoint d over d minus 2. What I've written here is just another way of saying that. And it just means that in a practical manner, what does it mean? Well, if I count all the integer points in ZD, such that the maximal function, when I apply it to a characteristic function of a finite subset f inside of ZD, and I look at when that's bigger than alpha, the number of such points is bounded by some constant times an appropriate power of alpha times the number of points that was in that finite subset I started with. Okay. This is just something from Lorentz theory, which I'm going to take for granted. If you don't know what it means to your restricted weak type, just take this as the definition. That's going to be fine for us. Okay, so it's equivalent to any other definition that you'll get. And now this is actually for all alpha between 0 and 1. Okay. So that's our first goal to prove. And as I said before, we're going to use the high-low method. Okay. And the way we do that is this high-low method, or the way I'm going to follow it, is from a paper of Ionescu. And what you do is, that's Alex Ionescu. And what you do is you insert some other cutoff, right? So psi was our fixed bump function, which is, just to remind everyone, psi is equal to 1 on minus 1 over 8 to 1 over 8 in every direction, and supported, so it's 0 outside of minus a fourth to a fourth in every direction. And when I throw in this extra parameter t, that's going to be between 0 and 1, so that T of lambda is smaller than lambda, or is it most as big as, sorry, T of square root lambda is at most as big as square root of lambda, but it's always going to be, say, bigger than 2. Once I do that, and I throw in this function, it means I've localized this localization even further. So what was the picture we had before? I take some modulus q, say q is equal to 3. And I had a little box inside of here that was of size basically about, had side lengths about 1/3. And inside of all of these, right? That's what, without this term, that's what's happening. So inside all of these boxes is where this measure is supported. But now when I throw in this extra T of lambda, it's going to take it's going to take an even smaller support. And if T is 1, then this is actually quite small. It's just a tiny little bubble inside these blue boxes. And inside that little bubble, I'm going to say are my low frequencies. Outside of that bubble, I'm going to say are my big frequencies. Right? Technically, for each square, each little subsquare has its definition of low and high. And due to the 1/q periodicity, this makes sense, right? And okay, so the way I did this is, or the way this is done, is you just squeeze in this factor. And because of this being 1, the product of this factor and this factor is actually just equal to this factor. Okay, by the way, I chose this to be greater than or equal to 2. And the fact that we have this is supported on minus 1/8 to 1/8, and is equal to 1 in there, and supported in minus 1/4 to 1/4. Great. And what I said was that the high frequency part is just going to be 1 minus that, which is just this right here. Okay, sorry, it's just going to be the complement of the low frequencies. And so that's just, in terms of this factor, that's just 1 minus that factor. Great. So that's how we define low and high as Fourier multipliers. Now, we need to define them as operators. And you just do that by taking the inverse Fourier transform of each of those pieces. And I call that big C right there. So little c is the Fourier multiplier, it's on the frequency side. Big C is the convolution operator corresponding to that. And you define your low piece for the C of lambda as just a sum over all the low pieces. Almost. There's a quick catch here. I actually need to talk about high and low in another respect. So going back to that, this definition of low and high is really only caring about, as I've tried to indicate by putting it next to the spherical measure, it's really just caring about what's happening in the real place. This is low in RD. But I actually want an Dilation picture of this. And so that needs to be what's happening modulo Q. Right? And you insert another parameter, which I'll call big Q. This is going to be a modulus that all my Q's go up to. And all the Q, little q, that are, so Q less than or equal to big Q, are low, whereas Q bigger than big Q are high. Okay, and this is in a Dilation sense. So the Dilation low part of my operator C lambda is now I sum up all the moduli up to big Q, all of their coprime parts, C of A Q lambda, but just the low part of those, which is in the Euclidean respect, with respect to RD. And then the high is everything else. It's all the big Q. That should be right here. Oh no, yeah, that is right. Yes, so I take all the high parts for all the small q, high with respect to RD. That's this first term. And then I throw in also just all the C of AQ for the big moduli. Okay, right. So this is all how Ionescu proceeded, and the main difference from his paper here is just adding on this Dilation perspective, understanding that there are two different ways to think of high and low. Well, there's an Dilation way to think of high and low. That means by looking in the real place and then for all the primes p-adically, which in this case just simplifies to having some parameter q that you can choose to be big or small for the moduli. Okay, that's the only contribution I've made in this setup right here, right? Is bringing to bear this perspective of low versus high frequencies, and it turns out to be an incredibly useful one in the area right now. So it's a perspective I've been putting forward for since at least 2014, and it is finally gaining traction, and that people are really starting to see this is a good way to think about a lot of these problems. 1 second. The light's turning off. Okay. Moving forward, now that we have our definitions of what a low operator is and what our high operator is, let's start proving some lemmas for them. Fix your thresholds, the big modulus q, and this other parameter t, that's just t stands for threshold. And we define the high pieces as above, right? Then we have the following L2 bound for the maximal function applied to each of these pieces. Okay, whenever you see a star here, it means what I've done is I've taken a sup over all lambda in n, right? So C star AQ high is just applied to a function x, is just defined as a sup over lambda in n of C lambda A Q F in absolute value. Oh, the high part, sorry. And technically, remember, this should be up to some big integer n that we'll let go to infinity, but we're glossing over that technical detail. Great. Now, whenever you see AQ low and a star with it, it's just the same thing, but with, if I have a low here. No, what's going on? Then it's the same definition. Okay, or the analogous definition, to be precise. All right. What was I saying? Well, I was just saying that when you look at these operators, C of AQ and the high part, and you form the maximal function over them, then on L2, you have the following good bound for it. Is at most Q inverse, where Q is the modulus, A over Q, and then times our threshold, T to the 1 minus D over 2. That allows you, whenever you sum up over Q, to obtain the following bound. So the high part is just, it's going to be a sum over this high part plus these pieces. And what I failed to write on this slide is that we also have the following bound, C star of A over Q from L2 to itself is at most, what would it be? Q to the minus D over 2. Okay, and we'll see the proof of that too. Great. So how do we prove these things? Well, we haven't made use of the transference lemma yet. So that's going to be basically what we do. Okay. Let's go through with it. There's one nice little trick that comes into this proof, and it's going to be the following observation. I can write each C of AQ. So C of AQ, my A looks a lot like a Q of lambda, as actually the composition of two operators. It's going to be T of lambda A over Q, composed with S of lambda A over Q. Let me tell you how these are defined. And let's go ahead and make this high for the moment. High. Okay, and high here. How do we do this? Well, let's look at the multiplier. I had my little c of lambda AQ, let's say high. At a point C was just this sum, M in ZD, G of AQ, M, and then, oops, these localizing factor and the spherical measure. Right? Okay, and when it's high, I also have this other factor here, psi of 2 QT root lambda C minus M over Q. Or no, sorry, minus M. And I told you that the product of this and this was just equal to the latter one. It's just equal to by the assumptions that I made. It's the same sort of self-reproducing formula we saw in the continuous lectures for the middle part of this course. So using that, I'm actually just going to write this as, I'm going to squeeze in another sum here. This is actually a sum over, oops, let's say N in ZD. That's an N, and that's an N. And why do we get to do that? Well, what happens if we multiply out this double sum now? I get a sum over M and N, both in ZD, and then times these terms and these terms. But because of this localizing factor, whenever N does not equal to M, these two are disjoint. And therefore, the product is 0. So the supports of those two functions are disjoint. Therefore, the product of those two functions is 0. And we just get that we must have an addition, M equals N, giving us what we had a moment ago. Okay, great. How are we going to make use of this? Now I get to factor this into two parts. This equals sum over M in ZD, GAQM, and then psi of QC minus M. That's my first part. And then my second part is sum over N in ZD, psi of QT square root lambda C minus N, and then D square root lambda C minus N over Q. I'll call this little s A over Q of lambda I, for instance, and call this other one little t of lambda A over Q. Oh, I did it for the low. I'm sorry. This should have been 1 minus this. Oh, crap. 1 minus that expression. 1 minus that expression. Yeah, let's just go back actually for a moment. I'm just going to write this for lows. So whatever I was saying, I was just describing for low. All right, that's how I can find this as a product of two low pieces. And when you look at the inverse Fourier transform of little s, that's going to be my big S, and the inverse Fourier transform of my little t will be the big T. And that just gives you composition of the two operators. Writing as a product, and converting that product into convolution gives it as a composition of two operators. Taking t to be size basically 1 over square root of lambda, you get the same definition without lows anywhere. Right, that's just C of AQ. And technically, you would insert just a factor of 2. So let me draw that right here. You would do something like this, just 2QC, or Q over 2, sorry. Q over 2. That's why we chose things to be supported not from -1/2 to 1/2 in every direction, but from -1/4 to 1/4 in every direction. Okay, it's because now the product of these two, they are supported in whenever this one is non-zero. Okay, and you get the same sort of thing down here. You get Q over 2. Okay, so that you can define these operators without the low parts at all. And you can also define the high parts in the same way, and it's a very similar analysis to these. Okay, I won't belabor the point, but what we do have now at the moment is each operator CAQ high of lambda is equal to T of lambda A over Q I, composed with S of lambda A over Q I. I could have written this as a composition in the other direction, switching these two, because on the Fourier side, these are just a product, and I could rewrite the product in the other direction, therefore giving composition in the other direction when I take the inverse Fourier transform. That's fine. It's going to be better for us to write it in this way. But I also want to point out that S of A over Q, okay, it relies on A and Q, but it has no dependence on lambda. Lambda doesn't appear anywhere over here. So actually, it's just S of AQ. But unfortunately, that dependence on lambda does appear on this side. Okay, in particular, it appears right here. Oops. Right here. However, it doesn't depend on A at all. It just depends on Q. So let's just get rid of that and leave it as a Q. Okay, so what I really have now is I have operators that look like this, TQ and a high part. Oops. And I don't have any dependence on lambda here, and I don't really have any high part to it either. It doesn't depend at all on the threshold T over here. Great. Now, when I take the supremum, this has a nice effect. If I take the supremum over lambda and n of C lambda A over Q, the high part, say, its absolute value, and I apply it to a function f, then I get the sup over lambda, of course, of T lambda Q high of S A over Q F, right? I actually have that it's the Maxwell function over just this part applied to this new function. Okay, so define this as T star A over Q I. Oh, sorry, that's just a Q. Q high. And again, this is applied to the function S A over Q F. What I'm going to do is I'm going to do two things now. I'm going to bound the L2 norm of this Maxwell function. and then the L2 norm of this function. Great. The high part is done via the transference principle, as you might guess. Let's see what it looks like again. It's each of my multipliers looks like the following. I have 1 minus psi of qt square root lambda c minus m times the Fourier transform of the spherical measure root lambda of c minus m over q. And oops, this is of the form where we can just apply the transference principle, the Magyar Stein Wainger transference principle. Okay. How do we do that? Well, we're going to, or why is that? It's because this right here is actually, you move, the way this measure was defined isotropically, right? This actually can be put in here, by which I mean, I could have written this in the first place as the following. So the Fourier transform of the surface measure on the unit sphere times square root of lambda times c minus m over q. Okay, and that puts us in a form to apply the Magyar Stein Wainger transference principle. Now, from our previous lectures, we saw that the Maxwell function corresponding to taking. So if I define this, if you didn't have m over q, okay, so if you were to say take m equal to 0 and q equal to 1 to get 1 minus psi of t root lambda c minus m, oh, sorry, not minus m, just c, all times the Fourier transform of the unit measure on the unit surface measure, surface measure on the unit sphere, root lambda c. If we look at this and call this the Fourier transform of a measure on the sphere, root lambda, call it the high one, then we had a bound for the Maxwell function for this guy on L2. What was that, buddy? That buddy said that the Maxwell function for, so if I look at, say, f on RD to C, and I take f convolved with d sigma root lambda high, and I took a sup over lambda from big lambda to twice big lambda. Actually, if we took a sup over all lambda positive, then this is a new Maxwell function. Let's call it, well, let's just call it T star. It should be technically have a high here because it's capture our dependence on T. Then this T star of F is bound in L2 with the bound that T star F on L2 is at most T to the 1 minus D over 2 times the L2 norm of F. Sorry, that's a little L2 of RD. Just this we proved a long time ago. Just believe that I've recalled it correctly and that we did it several weeks ago. Now I have this bound on RD, and I apply it in this form right here using the Magyar Stein Wainger transference principle. That tells me, so Magyar Stein Wainger transference or sampling says that we have T star Q I of F on L2 of ZD is at most T to the 1 minus D over 2 of F, oh, sorry, little f on L2 of ZD. Great, but my function here was actually SAQ of F, right? So, oops, I've not given myself enough room. So let's move over here and say, okay. So I have T star AQ, so OQ of SAQ of F in L2. And I know that's by the Magyar Stein Wainger transference principle at most T to the 1 minus D over 2 of SAQ F in L2. And now I want to estimate the L2 norm of this. Well, the way we do that is that's just at most by Planck-Ruehl's theorem, the L infinity norm of the Fourier transform. Oops. On the torus. And what do we know? Well, this is a combination of Gauss sums, a linear combination of Gauss sums. And these are normalized Gauss sums, which we've seen many times before. The absolute value of each Gauss sum is at most Q to the minus D over 2. Okay. Oh, I have made a huge fib. The Magyar Stein Wainger transference principle appeals slightly differently because I have this factor of Q that does appear in here with the transference. It actually implies that this is a Q times T to the 1 minus D over 2. That's because because I've thrown it in on this part. Okay. The right way to see that. Or how easy that is. Yeah, it's okay. So this is when Q is equal to 1. And I had this right here, this T root lambda of C. I actually am applying the transference principle a little bit differently than we would, because that was working well when I would multiply also by psi of QC minus M, but I'm applying the complement here. So I actually get this factor of Q that comes in with the T along the way. Yeah, it's a bit, it's a little subtle, but it comes in there, and that's the right way to apply the Magyar Stein Wainger transference principle on this piece. And now when we apply the Gauss sum bound here, so this should have been a Q, so 1 minus T, QT, the 1 minus D over 2. This will be at most Q to the Q times T, the 1 minus D over 2, times Q to the minus D over 2, times the L2 norm of F. And when you collect the right powers of Q, we get the bound that I claimed before, which is just this bound. When you don't have when you want to prove, when you don't have the high part and you just want to prove it for a big modulus Q, that's even easier than before, because you will use this separation principle right here, and separation trick, sorry, and no, back. And I've got this extra factor here that splits it into two very similar pieces. And you can apply the Magyar Stein Wainger transference principle very directly for these pieces. You don't pick up any factor of T because it's not present in any of the analysis. And you don't pick up any factor of Q either, because that's not paired with the T for the high part. But yeah, that is, you don't pick up a factor of Q when you do this transference part. However, when you look at the L2 norm for the S of AQ, given by this, you do pick up the Gauss bound, the Q to the minus D over 2 coming from this having size at most q to the minus d over 2. And so you just get the bound that I claimed right here. Probably should have led with that. Now, when you sum up overall a and q, they're all bigger than q, remember? Sorry, they're all bigger than big Q. They're about QAs they're about little QAs for every little q. And all those little q's are bigger than a big Q. So when you sum everything up, you get these bounds. Let's press on. Wait, are there any questions on that so far? I messed up a little bit the explanation of how to do the high parts. And I just reiterate that the Magyar Stein Wainger transference principle is very good when you have something of this shape. How was it? Let me get a cleaner copy. Magyar Stein Wainger transference principle is very good when you have something of this shape. Okay, ignoring momentarily this localizing factor. It's very easy to apply, and you just take the bounds from RD and put them right onto ZD after you incorporate what happens on L2 from doing the separation trick. But when you do add in this term, you have to be a little more attentive, and you do have to pick up the dependence on Q and T, on Q times T, when you transfer your results from RD to ZD. Okay, without going on to that for too much longer, let's move on to the low pieces. So we're going to get a complementary bound on L1. This exponent d over d minus 2 lies between 2 and 1 for all d bigger than or equal to 5. And so it's natural to try and interpolate bounds on L2 with bounds on L1, because in harmonic analysis, there are three very privileged exponents, p equals 1, 2, and infinity. 2, we use Fourier analysis on because L2 is just prime Fourier analysis, right? And then on L1, it's not so good for Fourier analysis, and so we're not going to use that here, really. We're going to take a more physical approach to understanding these operators. Okay, great. So I fixed my thresholds, T and Q again, and we're going to get a bound depending on those thresholds. If I fix an A over Q, a fraction A over Q, I have the following weak type 1,1 bounds. And they depend on Q, this little q, and T. Now, when that is a low frequency piece. And when I sum up over all those low frequency pieces, I get a bound that looks like Q times T inverse, because they're roughly Q squared things to sum up over. And I'd only saved one Q in this bound right here. Great. Let's see how to prove this. So the main part here is the following proposition, which tells us what the kernel of that convolution operator looks like. So the kernel is just the inverse Fourier transform of the multiplier, right? And the convolution operator was the inverse Fourier transform of the multiplier times the Fourier transform of your function. Fourier transform takes multiplication into convolution. So it's the kernel is the inverse Fourier transform of your multiplier. And then that gets involved with the inverse Fourier transform of a Fourier transform, which is just the original thing. Okay. And the expression we have we get a very concrete expression for the kernel at every point x inside of ZD. Let me remind you of this notation, this dilation notation. So when I look at, say I have a threshold T, I have infinity here. Well, let's take a P, a general exponent P, between 1 and infinity, including. And if I look at a point C, this is going to be T to the minus d over p times psi of c over t. When p is infinity, this is infinity, and this term just disappears because that exponent is 0, so it's going to be a 1. And these are nice notation because they have the following property. They intertwine with the Fourier operator in the following way. P composed of the Fourier transform is equal to you get this composition, right? I can move the Fourier transform in and out of the dilation operator, but when I do that, I change the dilation operator to a dual one. That means that this parameter t, which is always 0 or greater than 0 to dilate by, gets switched to t inverse, and the exponent p gets switched to p prime, where 1 over p plus 1 over p prime is equal to 1. Right. Now we need to prove this proposition. Take a moment to pause. I'm just going to start by writing out the inverse. I'm writing out the definition of the kernel. It is the inverse Fourier transform of a certain multiplier. Remember, there was a factor. I technically have a factor like this as well. C minus m times all of this, but that's trunked by this one. Let me go turn on the light again. Since their product is just the latter function, the one that's underlined, I'm just deleting the other function to really save space on the screen and mental space as well when calculating the inverse Fourier transform. Great. The way I'm going to do this is I'm going to write every m in ZD as q times n plus b, where n is an integer or an integer point ZD, and b is something in z mod q to the d. Okay, so this equals the integral over td, this character, and then I take a sum over b in z mod q to the d, and a sum over n in zd, g a q m, then psi of q t square root lambda c minus qn minus b, because that's m right there. And then what else? Fourier transform of this buddy minus n, oh, sorry, qn minus b over plus b over q. And we get to simplify this expression in a couple of ways. Oh, I didn't write this out. This is qn plus b down here. Recall that the Gauss sum only depends on what's happening mod b. Sorry, mod q. Only depends on qn plus b mod q. That's what this parameter right here is keeping track of. And we can see that also comes up over here. Qn minus q, sorry, qn over q is just n, right? And we get to rewrite all of this as follows. This equals the integral of, and I'm going to squeeze this character in all the way. So the integral of a double sum, so integral over td, sum over b and z mod q to the d, sum over zd, and then what, e of minus x dot c, g, a, q, and b now, depends on b, then psi is pretty much the same, minus q and minus b and then this inverse Fourier transform. Oh, crap. Oh, pen battery is low. Okay, not the, yeah, okay. Where was I? Yes, and then I have this expression. C minus N minus B over Q. Okay, what we'll do now is we can switch the order of integration with the sum right here, because those are just two compact spaces, and as long as everything else will be sufficiently well bounded, we're able to do that, and they will be, right? And also this sum doesn't depend on N at all, so it gets to come out along with that part. And yeah, that's all we get to do at the moment. Okay. So it's equal to the sum over B, Z mod Q to the D, integral. Oh, sorry, that doesn't come out with it. G of A, Q, B, integral E of X dot C, or minus that, TD sum over N in ZD. And the rest again, psi. All integrated with respect to DC. And what do? You just, well, okay, if I put this back inside, all I'm going to do is I'm going to unfold this integral over the torus with a sum over N and ZD. By that, I mean I'm going to unfold it. This is actually just equal to the integral over RD. Okay. Making use of that. This is unperiodizing things. Have you seen periodizing before? Then I get a sum over B in Z mod Q to the D. And my Gauss sums coming into play always. Times the integral over RD of what? Psi of Q T root lambda. And then I get a C minus B here, and a D twiddle root lambda times C minus B over Q. Yeah. Phew. And we see that we have an integral now on RD. And now I can play the usual tricks with localized, I have these dilations coming into play here and here, and I have a shift by B happening here as well that I get to do. Okay, let's use those and rewrite this a little bit further as it's the same sum. All right, that part again. It's going to be an integral over RD. Oh, I forgot the factor of E minus X dot C minus, E of minus X dot C. And then I have this dilation operator on infinity. And then it's going to be QT inverse of, applied to psi at lambda C minus B. And then I have the same thing, or no. Instead of D sigma root lambda C minus B over Q. I forgot the root lambda. No, root lambda C. Let's make that look prettier. This should be a root lambda times C. Brilliant. Okay. And when you don't mess things up like I did, just now, that should be a b over q, because I put the q out over here and I have to take it out of the whole expression. So now I have xc minus b over q here. And this is all integrated with respect to dc. I can just shift by b over q, right? So I add c goes to c plus b over q. Okay, that gets rid of this, gets rid of this. It comes up over here plus b over q. But then I can pull that out, and that's actually a sum over b and z mod q. So d, g, a, q, b, e of minus b over q, right? An integral over rd, e of minus x dot c, this dilated localization psi, and integrated with respect to c. Woo! Okay, getting somewhere. Now the whole point will be to understand this part and this part. You see that they don't interact with each other anymore. They're two different parts. I'm going to just leave as an exercise to the reader for them to show that this part is actually equal to e of q of x, no, q of b, what did I say? I sum over b times there should be an x here, sorry, x times that, because there's the x coming there, right? So this is q of x, a q of x over b, over q, sorry. This is just an inverse Fourier transform on z mod q to the d. Basically, what you see is when you take the Fourier transform of this, you get the Gauss sum, this on z mod q to the d, and now we've gotten an inverse Fourier transform here, and that just returns you to this right here. Okay, nothing deep is going on there. That's why I'm going to skip over it. But we do really need to understand what's coming into play right here. And I've singled out right now these dilated parts of square root of lambda in the expressions right there. So this is where I want to, so when you do the inverse Fourier transform, right, you end up getting, I get this last expression is the inverse Fourier transform of what, a certain dilation. Times, or convolved with the inverse Fourier transform of this measure, which is the square root lambda. Well, that's this Fourier transform, right? So it's the inverse Fourier transform on each of these, and that just is equal to, well, it'll be dilation of the one norm, and then qt to the inverse, which is just a +1, and that's a certain psi function, which I'm going to leave here for a moment, some space. I haven't quite treated this properly yet, but it's going to be convolved with just this spherical measure. Okay. Now, I really just actually want to, think about this as being coupled with the spherical measure. That's not quite something I can do because the spherical measure was defined independently of it. But what we can see is the following. Whenever I could take, and I could have put the dilations all together. So I had in the first place a qt root lambda inverse of psi times No, let me do it this way, sorry. I had this overall dilation on the outside by square root of lambda. Great. And I'll make use of that now. So I actually had a dilation, a QT inverse, infinity, and the psi. So let me get myself enough room here. As soon as this calculation is completed, we'll take a break, but give me a moment. So I have actually a dilation by root lambda inverse, infinity, applied to the product. And then I'm going to take the inverse Fourier transform of this whole thing. Right, so moving it forward or through, I actually get a dilation on L1 of root lambda composed with the Fourier transform of this part. And that's actually equal to, well, dilation, L1 dilation. And then I move the Fourier transform through, like I said before. And this will be dilation, an L1 dilation by QT of psi, convolved with the unit spherical measure. Okay, and what we really have to study now is just this. Okay, but when you unwind that notation, what you end up getting is you end up getting this right here, right? Because that square root of lambda, the L1 dilation, is exactly, you're going to be picking up this factor here, and then you're having that come into play there as well. But the, yeah, and there. So when you plug in this definition for p equals 1, you get exactly this expression. Okay, that's a good point to stop for now. Let's take a 10-minute break. And I'll come through and I'll show how this proposition will imply this lemma, and then how you combine these two lemmas to get the theorem we want, and then how we use that theorem to get the Magyar Stein Wainger theorem. Right. Were there any quick questions before I pause the recording? All right, well, I'll see you all in a few minutes.